Hi, I'm Ahmed Daud, and in this session we will see mean squared error and root mean squared error. So, from the last sessions we were doing evaluation metrics for the regression models, and last time we have seen mean absolute error. Okay, we have seen the flaw in the mean absolute error was the just one that we cannot differentiate the mean absolute error function due to the absolute function involved in the MSE, MAE, sorry. Now in this session we will see mean squared error and root mean squared error. You are already familiar with these errors. Just it will be a recap and some of the pros and cons of that errors we will discuss here. Last time I have told you that during training process our aim is not to have such a model, and we are not calculating the errors for the model. We are actually calculating the errors just for the sake of the training of the model. Okay, if we are using the model root mean square error or any other type of error, our purpose is to train the model and have to reach at the minimum position. Okay, have to reach at the minimum position where the error is minimum. So here the purpose is not to show or to explain the model, how much good is model or how much bad is model. The purpose is to just train the model and explain and try to reach the minimum position of the error. So that's why we usually use the such type of errors, such type of you can say metrics in the training process that can bear and that can make the training purpose easy. Like in the sum of squared part, sum of squared error, we sum of squared error used in training phase, and the sum of squared error has a very has a convex function which is differentiable at each point. So if I will write here, SSE is convex function which is differentiable at each point. So we have used that. Due to this nature of SSC we have used, either it is not you can say a good measure to explain the you can say goodness of the model. It cannot it may be not a good metric, but for the training purpose it is good. We will explore that also today. So mean squared error, it's just a mean of SSE. Okay, you can say the mean of SSE is a MSE, which is mean squared error. And if I will write here in this way, y minus y cap square, for each point we will add and just take the mean. Okay, this is mean squared error. Now there are some flaws in it. The first one that we will discuss here, it is sensitive to outliers. How it is sensitive to outliers, I will show you here also. But before that, due to squaring nature, if I write here, due to squaring nature, this mean squared error is sensitive to outlier. Okay, okay, I will show you here. So let's say this is our actual value, this is our actual value, this is our predicted value, this is the difference between them. If I will use, okay, this is the difference between them. Now here, this is the actual value. Sorry, I should use smaller one. Okay, here you can say this is the difference between the actual and the prediction. In this way there is some difference, some a little bit here. Okay, but we are taking square here, so because of taking square it will become in this way. Okay, this will become like a squares. Okay, it is just because of we are taking square. Now we will add these squares and then divide by number of points, like 5 points, that we usually call MSE, mean squared error. Now how it is sensitive to outlier? Let's say if I will use this one. Okay, let's say there is a 1 point which is outlier. Let's say this is outlier. Okay, now this is actual value and our prediction is something here. This is our prediction, but when you will take a square of it, you can understand how bigger this area is. Now when we will add this area, while we are adding all the differences here, all the squared errors, when we will add this square error also, it will overestimate the error of your model, or you can say it overestimate the badness of your model. Overestimate the badness of your model. However, your model is not too bad because this effect is just due to 1 point, while all other 5 points are near to the your but are 5 actual points or actual values of 5 points are near to the predictions. There is just one value which is far away from the prediction. Due to just one value, it is overestimating the badness of model. It is saying that our model is so bad, but actually it is not so much bad. How much mean square error is describing here. Okay, due to just squaring the term, due to this square term. Okay, and in the same way, if the value is less than 1, if the difference, let's say let's say this difference is less than 1, then it underestimate the badness of the model. Okay, so in this way you can say this is not so much good when we are using it as a evaluation metric. Okay, this means squared error. Now the second flaw you can say here, it can be that uh, let's say your MSC here is 4.8. Let's say, for example, I am saying here. Now 4.8, you cannot explain this 4.8 as like you are explaining in case of MAE, because 4.8 has not the same unit as your data have. Because you are squaring here, so this 4.8 is actually square here. To explain this, how much error your model is giving in the context of your target column, you have to take a square root. Then you can say that let's say 2. Then you can explain that your model is giving here 2.2 lakh error, or you can say it is giving mean square error 2.2 lakh. Okay, now the second issue you can say here, second issue can be its explainability. When you have to explain the model, you have not same unit as your target variable have. Okay, this is in the case of mean error. And one of the biggest advantage you can say here is this mean square error, okay, is differentiable at each point. Differentiable at each point of, okay, this function is differentiable. Now maybe some of you have a question in their minds that mean square error we have discussed here, but during training process we are using sum of squared error. Why? I told you last time also that in the training purpose we are not actually uh, checking that how our model and how we have to explain the error of the model. The purpose is was there, or in the training purpose, the purpose is usually to get a minimum error, to get the parameters that are at the minimum position. Okay, so if let's say where your MSE is minimum, your sum of squared also at that position will be minimum. I am saying in this way, let's say your MSE is minimum at some these parameters. Okay, then there must be SSE is also minimum at these parameters, because you are just here just a division in this case of mean. Okay, so for the simplicity of the training we usually use this type of error function in the training phase, but in the testing phase or in the prediction phase we want such a model, such a error function which is good in case of explainability, and not over underestimate the badness or goodness of the model. So here okay, so you have seen this error function multiple times. Now we will see root mean square. Now root mean square error. Okay, so for the case of root mean square error, it is just as you can say RMSC. It's just a square root of MSC. Okay, it's just a square root of mean square error. Okay, there is not a much difference. It's just a root of mean square error. Now maybe you have a question in your mind, if it is so similar to mean square error, why we are using this root mean square error, or why we have this one. Okay, the advantage over mean square error is that in the case of explainability, okay, when you have RMSC, here RMSC is equal to, let's say, 0.13, then you can say your model is giving you 0.13 lakh. Okay, or you can say on average your model is giving the prediction which is away from the actual is 0.13 lakh. Okay, you can explain this RMSC, explain in the context of target variable. Okay, you can explain in the same context, because we have um, square term here, and after the, addition or after the processing of square addition of these square values, we are again taking the root, okay, to get this same unit. Okay, this is the advantage over mean square error. Now the same disadvantage that mean square error is have, root mean square also have, is this one, that it is also sensitive to outliers, because when you are first squaring the errors and differences, or you can say was to increase a lot, or you can say overestimate your error, again when you are taking root cannot balance the squared error. Okay, first you have squared your values, squared your differences, it it increase a lot in your error. Okay, so you can say penalize your outliers. So same disadvantage, that it is sensitive to outlier. Here I can say this is disadvantage. Now the third one is that if you have in your mind, can we use this function RMSE as a loss function in the training phase? Yes, you can use this one. But if MSC, SSE, RMSE can give you the same result, same parameters, okay, can give you the same result, then why we are using some complex, like root mean square has two computations more as compared to SSE, like one is square root, one is divided by the number of samples. Okay, so why we will use that RMSE? So instead we usually prefer SSE in the training phase. Okay, in the training phase our purpose is not to explain the model errors, or you can explain the how model is good or bad, The purpose is to reach at the minimum position. Okay, we have to reach at this position. So that's why we usually use SSC, or SSE is preferable in the case of training phase. So here you have seen this. This is very similar to the MSE. Just one advantage that I have told you here. Explainability here is the advantage. Okay, explainability. Now, when you will see this one, we will just jump to the documentation of the mean squared error provided by the Scikit-Learn. So we will use simply that mean square error by importing from sklearn.metric. Here you can see mean square error. I have passed here actual values. These are the predicted values, and the mean square error here, it is giving us 0.018. Okay. Now, when you have multiple models and you want to compare, you can compare in that case. But here, if you want to see like, this is mean square error. Okay. If I will say you that explain this mean square error in terms of target variable. How you will explain? It will be not easy for you to explain that. Before to explain that, you will have to take the square root of that, because this 0.018 lag square, it is not lag. But in the case of root mean square error, how you can calculate the root mean square error is the very simple. In the parameters of mean square error, here the last parameter, which is squared. So if true, returns MSE. If false, then returns root mean square error. Okay, you just make here the squared is equal to false, you will get RMSE. Now this is 0.13. You can say on average your model is giving the prediction 0.13 lag away from your actual values. Okay, so you can say the on average the difference between the actual values and the predictions is 0.13 lag. Okay, so here you can explain easily as compared to mean square error. Okay, and for the sake of implementing that, you can see it is very easy. And if you want to use without the library, you want to do by yourself, you can simply do that like we did for the case of mean square error. Okay, instead of just we have taken here the absolute values, uh, where we have taken this one. Yeah, here we have taken the absolute value ABS. We have taken the absolute function. You can use here the square function, or you can simply here square this column, and you will get hopefully the mean square error. And at the end of mean square error, you can if you will take the root of mean square error, maybe you will get root RMSE. Okay, so I hope this session is simple. I hope it should be a simple for you, because we have discussed sum of squared error multiple times, and mean square error, root mean square error, just the same. We have just visualized or analyzed just two aspects. One is sensitivity to outliers, and second one is explainability of both. Okay, and the third one that I have explained to you why we usually prefer SSE in the training phase is that because these SSC mean square, root mean square can be used, because these functions are differentiable at each point and give you the same result. So for the sake of simplicity or easy computation, we usually prefer SSE in the training phase. So I hope you enjoyed this session. In the next session, we will see some important evaluation metric of the regression model, and Scikit-Learn also use during the in its linear regression module the same metric that we will learn theoretically in the next session, and we will also implement it practically. So for now, thank you.